All right, getting a lot of questions for 32. So we're going to look at 32 next. An explosion breaks an object into two pieces, one of which has 1.5 times the mass of the other. If 705 or 7,500 joules of energy were released in the explosion, how much kinetic energy did each piece acquire? All right. So let's see here. One of them has 1.5 mass of the of the other. So let's say mass 1. Let's say that's the bigger one. Has 1.5 times the mass 2. All right, very well. And this explosion happens, and we got this much energy that's being released. So we call that the total energy of the system. Energy final, if it matters, but we'll see. How much kinetic energy did each piece acquire? So they want to know, like, how does the energy of 1 compare to the energy of 2? Of course, we're talking kinetic energy, right? Kinetic energy of 1. No, they don't say they have the equal. They want to know what each one is. So how does the kinetic energy of 1 compare and the kinetic energy of 2 compare? All right. Let's see here. Well, it does not say totally inelastic collision. The system, it's sitting still at first, right? Initial velocity of everything in here is 0 starting off. So my momentum of the system should be 0 as long as everything's conserved before and after. Doesn't say anything about impulse, doesn't say anything about anything else. So we're going to go with collision is elastic. Or I'm sorry, momentum is conserved. It definitely is going to be inelastic, though, because we have energy being added, though. All right, so if momentum of the system should be 0 both before and after this event, right? So, and if I have two particles of something that are like stuck together and pow, and get some explosion, and one piece goes off this way, and the other piece goes this way. If it starts with 0 and this is conserved, then my final momentum should also be 0, right? Because of conservation. So if I'm only looking at two pieces, then I'm expecting the momentum of one piece to basically be equal and opposite of the momentum of the other piece. Their strengths are the same. We definitely could say that. One would have to be the opposite of the other, though, because they both end up being 0. Everything's conserved, nothing changes. Okay. So I'm going to say that the momentum of 1 is equal to the momentum of 2. That's mass 1 times velocity of 1 is equal to mass 2 times velocity of 2. Okay. We know that mass 1 is equal to 1.5 times the size of mass 2. So I'm going to replace mass 1. I'm going to put 1.5 times m2 in its place. All right, so I can factor that out, right? Divide both sides by m2. And so what I'll see is that the first velocity times 1.5 is equal to the second velocity. All right, so the second one will be going 1.5 times faster than the first piece. Okay. Let's see what we know about energy stuff. So we had no energy to begin with. We had some energy afterwards. It's 7,500 total, right? So the total energy of the system here is going to be 7,500, looking after this event. And that energy is coming from the kinetic energy of the first and the kinetic energy of the second. If I were to have expressions for these, well, yeah, let's just do the expressions for the individual pieces here. So the kinetic energy of the first one would be 1/2 m1 times v1 squared, right? The kinetic energy of the second one would be 1/2 mass 2 times velocity 2 squared. Now, I know that, see, the mass 1 is the bigger mass, right? Mass 1 is 1.5 times the mass of mass 2. So whenever I have mass, let's see, let's make this a little bit easier. Let's look at the mass 1 statement. And instead of saying mass 1, I'm going to put instead 1.5 mass 2. So I can rewrite kinetic energy of 1 is equal to 1/2 of the value of mass 1. What is that? 1.5 times mass 2. Still times the 1's velocity. Okay. All right. And when it comes to velocity, I see over here velocity 2 is 1.5 times the mass of the velocity of v1. So let's see here. That's v1. I'm going to make one more line to this and say v2 divided by 1.5. And I'm going to plug that in right here. So KE1 becomes 1/2 1.5 the mass of 2 times velocity of 1. Well, what's velocity 1? V2 divided by 1.5. That number gets squared. So now I'm going to look at, I know the addition of these two is total, and I got that number. So let's see, K and now we've got two different expressions for KE1. We got a different expression for KE1 than we had previously. So still tuning into this idea here, where the two energies added together is still my total. Just rewriting this for instructional purposes. Now I'm going to use the new expressions I have. KE1, what is that? 1/2, 1.5, M2. I'm going to break apart this ratio. I'm going to write it as V2 squared 1 over 1.5 squared. All of that is KE1. I just used that expression right there. That's all I did. And KE2, there it is. 1/2 mass 2 mass of 2 times the velocity of 2 squared. Don't forget, I know this number, the E total. I see a lot of similar factors here. In this term, we have 1/2. We have M2. And we also have V2 squared. So watch this. That's one energy there, and that's the other energy here. I'm going to factor out 1/2 from both. I'm going to factor out the mass 2 from both. I'm going to factor out velocity 2 squared from both, which leaves me on the inside with half goes away, 1.5. Mass 2 goes away, V2 squared goes away, 1 over 1.5, whoops, 1.5 squared, right? The second term is 1/2 M2 V2 squared. It's the same thing, isn't it? So if I factor that all out, what does it get left with? 1. This expression right here, what is that? 1/2 of the second mass times the second velocity squared. What is that? That's the KE of 2. what is inside this parentheses. This is 1/2 divided by 1/2 divided by 1/2. I'm sorry, 1.5. It's 1.5 plus 1. So, 1.5, take the reciprocal. Well, 1 divided by 1.5 equals, okay, plus 1 equals. So I'm reading here that the total energy is equal to 1.66667 KE2. Is that right? Yes. Okay. Such that, remember the original purpose was supposed to find these KEs, right? I now know that KE2 is equal to the total energy divided by 1.6667. And I know this value, and that's a constant, so I can just plug that in. This was 7,500 joules divided by 1.66667. So the second kinetic energy, 100 divided by 1.2. Wait, that's too many digits. Well, it kind of doesn't matter. 1 point. Yeah, it kind of really doesn't matter. I use 6 digits, sue me. And now I'm messing it up. 1.66667. There we go. 1, 2, 3, 4, 1, 2, 3, 4. It kind of doesn't matter. Right about 4,500. I got 4,499.99. So we're going to call that 4,500 joules. And the total was 7,500, which is the two energies added together, right? The KE1 plus the KE2. So KE1 will be the total energy minus that KE2 we just solved for. 7,500 joules minus 4,500 joules. So the first NASA's kinetic energy after the explosion should be 3,000, looks like. 3,000 joules. KE1, KE2. All right, there you go.